We've been talking about chemical equilibria and the equilibrium constant and how that gives us an idea of how far the reaction proceeds in the forward direction. What if the reaction mixture is not at equilibrium and there are reactants and products present? How can we predict which direction the reaction is going to go? We're going to use something called the reaction quotient, which is Q with a C or a P, depending on whether it's concentration or pressure. The reaction quotient is calculated the same way as the equilibrium constant, except that the reaction is not at equilibrium. So it is a temporary value. That's why it's not a constant. It's a reaction quotient, and that's going to tell us where the reaction is in its process towards equilibrium. So just like for the equilibrium constant, we're going to calculate it in the same way, with the concentrations of the products raised to their coefficients divided by the concentrations of the reactants raised to their coefficients. At equilibrium, the reaction quotient will equal the equilibrium constant. So let's look at this. Okay, here we have just A. So we're looking at the reaction. A goes to B, very simple. So A is the blue ones and red is the B is the red ones. Yeah, I would have done that the other way around, but whatever. So here we have all A. And so, of course, the reaction can only go in the forward direction, right? Here is our equilibrium constant. This is the place where the quotient is equal to the equilibrium constant. If we calculate the reaction quotient, which here is the concentration of B over A, initially we're going to see that this is smaller than K, and the reaction will proceed in a way that Q becomes closer to K. If we start up here, where the reaction quotient is larger than K, then the reaction will proceed in the reverse direction until the reaction quotient and K are the same. Did that make any sense? I will try to explain that a little differently. It's one of those things that when you can see it, how do you describe the color blue to someone, right? It's hard.
It's just blue.
Yeah. Okay, let's try a different way. Nothing's coming to me. If I could do voices, maybe I'd just do the same explanation in a different voice. No. Yeah. Okay, well, initially, we only have A. And so here, the reaction quotient is going to be 0 because the concentration of B is 0 divided by whatever the concentration of A is, it's still 0. As the reaction proceeds, the concentration of B is increasing and the concentration of A is decreasing, right? So the quotient is going up as the reaction proceeds. Does that make sense? Yes, it is like a car wash. You get cleaner as you go through it.
You start with all the dirt, which is like your reactants. And then
I'm afraid that's going to break down, though, because this is a reversible reaction.
you could just go through.
No.
Dry
drive through all the water with all the mud when you're done. All over
You know, I'll have to think about that one. I'll have to think about that one later. When we are up here where we have almost entirely the product B, then the reaction will go in the reverse direction because this is past its equilibrium point. This here, where the blue and the red lines intersect, for this particular reaction is where the equilibrium constant is. So 1.45, the ratio of B to A at 1.45, that's where it's at equilibrium. So if the quotient is larger, that means there's more A, say A and circle B. There's more B than A, and so in order to get to equilibrium, the reaction will have to go in the reverse direction so that some of the B gets used up and some A gets reformed, and as that happens, the reaction quotient gets smaller. Was that any better? Okay. So the reaction quotient is telling us which direction the reaction will proceed. We're going to proceed in a direction that brings the quotient closer to the equilibrium constant.
Can you think of it like an actual scale where you're like balancing two things?
Can you think of it as a scale where you're balancing two things?
Or one is reactants, one is reductants.
Like a
I think you kind of could.
Yeah.
Yeah. I do think of equilibrium a lot as like a teeter-totter, right? And so, you know, if it's low on this side, the teeter-totter has to get to its equilibrium point, and so in order for that to happen, we have to go this way. So the reaction quotient, again, calculated the same way as the equilibrium constant. The difference is that we don't have to be at equilibrium. It's just wherever the reaction is. So if the reaction quotient is equal to K, that means the reaction is at equilibrium. If the reaction quotient is smaller than K, that means the reaction is going to go towards the products to increase the reaction quotient until it equals K. And if Q is larger than K, the reaction will go in the reverse direction so that Q gets closer and closer to K. So at any given temperature, there's only one value for the equilibrium constant. The quotient could have all kinds of different values depending on the current state of the reaction. So that's going to change, but K is constant. Consider the reaction and its equilibrium constant. So here we have N2O4 reacting to form 2NO2. And here's the equilibrium constant. It's at some temperature. We don't need to know what that is. So a reaction mixture contains these concentrations of reactant and product. Calculate the the reaction quotient and determine the direction in which the reaction will proceed. So looking at this equilibrium constant, this is a small number, right? And so we could predict that the amount of reactants is probably going to have to be larger than the amount of products. But in terms of exactly how much, it can get a little iffy, especially if you have some coefficients in there and powers. So that's where the reaction quotient comes in. So the reaction quotient is going to equal the concentration of the products, NO2, and that one's squared, divided by the concentration of the reactants. So we're going to put in the values that were given here, so 0.0255, and that'll be squared, divided by 0.0331, and we'll get a value for that. So this is 0.019645. And then we need to ask ourselves, is this number larger or smaller than that one? It can get a little tricky to compare numbers in decimal and scientific notation. I'm just going to write the other one in decimal notation. Might be a little clearer. So that's K, and this is Q. So Q is larger than K. The reaction is going to go in a direction that will cause Q to become closer to K, because that's the goal. It's going to move until Q and K are equal. Q is too big. That means we need to make the numerator smaller and the denominator larger, right? So we need to reduce the product concentration and increase the reactant concentration. So this is going to go in the reverse direction. Does that make sense? Anybody have a question? So here's a conceptual question. Looking at that same reaction, this initially contains N2O4 and NO2 in their standard states. The standard state for a gas is a pressure of 1 atmosphere. So partial pressure for each of these gases is 1 atmosphere. And they're telling us that the equilibrium constant in terms of pressure is equal to 0.15. So which statement is true of the reaction mixture before anything happens? Q is equal to K, Q is less than K, Q is greater than K. Well, how do we calculate Q? It's going to be the same as we did in the previous one, except here it's going to be QP, right? It's the pressure of the product squared divided by the pressure of the reactant. Well, we don't really need to do any math there because they're both 1. So then Q is equal to 1 here. So is the reaction going to go forward or reverse? It's going to go in reverse because, again, Q is larger than the equilibrium constant, and the way it can become smaller is for this pressure to reduce and this pressure to increase. So the answer then is C. Any questions? Yes?
So this works even with, so it could work with pressure, molarity?
Yeah, we can do it in terms of pressure or in terms of molarity. You need to use the correct equilibrium constant to compare it, but as we learned in earlier, you can convert a KP to a KC and vice versa. Yeah. Any other questions?